Let's go through an example of a delay model. So let's start out, sketch a 3-input NAND gate, all of the transistors, and add transistor widths that are chosen to try and achieve the same effective rise and fall resistances that are equal to a unit inverter, like we've been looking at. So pause here and do that and restart after you're done. This is what your 3-input NAND gate would look like. So now we have the NMOS devices and the PMOS devices. Now, if we want to size the NMOS devices such that there would be an equal resistance to a inverter down to ground, we would need to make sure previously our inverter down to ground had a unit resistance of 1, and we want to keep that the same. So if we have 3 in series, we would need to have each NMOS device would have to have a unit size of 3. That way the 3 in series would have a resistance that would be 1/3 of that, or or it would take the resistance of 3, since the wider device is smaller resistance, so a size of 3 would give us a resistance of R/3, and 3 of them in series with each other would be a total resistance of R. For PMOS, the previous size for a inverter was a size of 2 for the PMOS. Since any one of those only one of them might be turned on, so we want the size of each of them to be a size of 2. So that's where we get this for our PMOS devices and NMOS device sizes. After sizing a 3-input NAND gate to give us the pull-down stack, now if the full pull-down stack is on, the equivalent resistance in our model from output to ground is going to be equal to if we had a single 1 size NMOS. So three devices in series that are size 3 have an equivalent resistance of a size 1, a single size 1. And the PMOS devices, since they're each in parallel, we're concerned with the worst case where only one of them is on, so a single one, each one needs to be size 2 in order to be equivalent to the inverter that had a PMOS of size 2. Now let's annotate this with the gate and diffusion capacitance that we wind up getting from this type of device. So you can see for each of the PMOS, the source, drain, and gate are all 2 times C, since they're unit 2 size transistors. And for the NMOS, each of the devices is 3 times the capacitance value of a unit device because they're a size 3 transistor. So when we take all of that and sum them together and basically make it simplified by adding all the capacitors that are in parallel with each other together and just lumping a single capacitor, we find that at each of the inputs we have 5 times the capacitance, or 5C, and at our output we have 9C, and then we also have in between each of the NMOS devices in the pull-down stack we have an additional 3C. This compares to if we had a single inverter with a 2 size PMOS and a 1 size NMOS. Our input to a single size inverter would be only 3C instead of 5C for each of these inputs, and the output would only be 3C instead of 9C for our output, and then having an additional 6C in the pull-down stack. So you can see, in order to make something that might have a similar resistive profile to a unit size inverter, we wind up with a lot more capacitance on this in order to get kind of an equivalent behavior, or trying to get an equivalent behavior to an inverter. So from the previous slide, you saw when we had the pull-down network, the N devices were in series with each other. The on transistors looked like resistors, but the pull-down network having three NMOS in series with each other, that can actually be modeled as an RC ladder. So when we replace the transistors with an R and a C, that lower transistor looked like it was an resistance value down to ground, R1, and then its first capacitance is C1. The next transistor was an R2 hooked up to and it would have a value of C2 hooked up to the next transistor R3 to C3. So for each transistor in series with each other, you can see that it looks like it's an RC connection, and it looks like it's an RC ladder. So when you take the propagation delay through that RC ladder, you can see that it's not just a function of R1 C1 multiplied by some constant K, for example. So if you had three in series with each other, you wouldn't just take R1 C1 times 3, because once you get to the second device, you now have R1 plus R2 in series with each other times C2, and when you get to the third device, it would be R1 plus R2 plus R3 times C3. And if you have multiple, you go up to N in series with each other, you have R1 plus blah 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 up to plus Rn times Cn at the output. So you can see as like the Elmore delay of an RC ladder gets slower and slower, not just by a linear amount as you add additional devices in series, it becomes something slower than linear. So now let's estimate, continuing this example, estimate what our worst case rising and falling delay is for a 3-input NAND. And we need to, obviously, if we have the 3-input NAND here, it should be driving something, so it should have some receiver that's receiving its output. And in this case, let's say we're driving H copies of identical 3-input NAND gates. So it has a load for each receiving gate. There's a size 2 PMOS and a size 3 NMOS that will be receiving it times H copies. So seen over on the right hand side, this would be the model that you would want to use to estimate your worst case rising and falling delay, where you have the model of the gate itself with its 9C capacitance. On the 9C is coming from the gates connected inside the 3-input NAND gate, and then where Y says that there's this 5HC there, that's because there's H receiving gates, and each receiving gate has 5 times C capacitance of the gates, because there's a size 3 and size 2 transistor receiving inside each gate. So go try to calculate what is your rising delay, worst case rising propagation delay, and worst case falling propagation delay. I'll give you a second to do that, and you can pause this and try to do that right now, and then we'll go through the answer. So first let's look at if we're trying to do the rising propagation delay. In this case, the worst case is if only one of the PMOS is turned on. We don't have 3 of them turned on in parallel. So 3 turned on in parallel would be the best case rising delay. Worst case would be 1 PMOS device turned on. So that means we have 1 R value connected up to VCC, and we could have the top two NMOS devices turned on, but we can't have a stack turned on all the way to ground because we're trying to pull up to VCC. So two of those NMOS devices could be turned on. So that's why it's showing an R over 3 value connected to a 3C, and then another R over 3 value connected to another 3C, and then the last R over 3 is not connected to anything because it's turned off. But the output is connected to the 9 plus 5H times C, because there's 9C plus 5H times C. So the total capacitance is 9 plus 5H times C for capacitance. So this propagation delay would be that capacitance value times the resistance value of R, and we get our propagation delay for rising is 9 plus 5H times RC. Now let's look at the same thing for the falling propagation delay. So in this case, we have all of the PMOS transistors turned off, so there is no connection at all up to VCC. The 3 NMOS transistors are connected and turned on, so we have at the output a 9 plus 5H times C, but then we have for each intermediate node, we have a 3C factor in there. So as we were saying with the previous foil, the Elmore delay for an RC ladder here comes out to be, for the first part that's closest to ground, we have a resistance of R over 3 that needs to drive a 3C value. So we have 3C times R over 3. Now going through the second part of the resistive ladder, we have another 3C that's now being driven by 2 resistors in series with each other. Each is R over 3, so we have our R over 3 plus R over 3 driving the second value of 3C. And then finally, we have driving the output node, we have 3 values of resistance, R over 3, in series with each other. So we add those up, R over 3 times 3, or plus R over 3 plus R over 3, times the value of the output capacitance, which is 9 plus 5H times C. Take that entire equation, and we wind up with 12 plus 5H over quantity times RC. And so you can see the rising delay is going to be smaller than the falling delay in this case, but they'll be relatively close to each other. Examining the delay of the previous 3-input NAND gate, you can see that the delay has 2 parts to it. The first part is our parasitic delay. That's the delay caused by the driving gate itself if you had no load attached to it. So that delay in this particular case for rising, you can see it was 9 times RC, and for the falling, it's 12 times RC. And again, this is independent of load. If you had no load attached to it, that's what your delay would be. Then there's also the effort delay. The effort delay is, in this case, the 5H times RC. It's the number of gates that you're trying to drive, or the total load outside of the driving gate itself. And this, of course, is proportional to the load capacitance. What is the total load on the gate that's being driven outside of the gate? And so keep in mind that that's always true of any time you're trying to have a gate connected to something. You have a parasitic independent of load delay and some additional delay based on how many things you're trying to drive and how much load you place on it outside of the gate. The previous couple of slides were talking about the propagation delay for this 3-input NAND gate. Let's now talk about the contamination delay. As I mentioned before, the propagation delay is the worst case time delay that you get contamination delay is the best case delay that you can get. And this can sometimes be substantially less than the propagation delay. For example, in this particular 3-input NAND gate, if we had all 3 inputs were high and we had all 3 inputs fall simultaneously, so that they're switching at the exact same time, that would cause all 3 PMOS devices to turn on at the same time, which greatly increases our drive strength pulling up to VDD. So in this case, we would have something that looks like down in the lower left corner, where we have 3 resistors R in parallel trying to drive the output capacitance load of 9 plus 5H times C. So that same load is now being driven by about 1/3 the effective resistance value. So instead of the contamination delay parameter would be the capacitance times R over 3, and the overall functional value coming out would be 3 plus 5/3 times H times RC. So our contamination delay might be approximately 1/3 the value of our propagation delay. So that's can be a vastly different value. So one more thing we need to talk about relative to this topic is we've been assuming up until now that every gate is individually laid out, and so our diffusion capacitance that we're putting that we're counting for each gate is the same for every time we add a transistor. We're going to add the same amount of capacitance value. But in practice, we don't wind up laying things out like that. We try to minimize diffusion area wherever we can. For example, below you can see some good layout for a NAND 3, where we have 3 PMOS transistors, and the rightmost PMOS transistor has a contact to VDD on its left side, and the output of that transistor is on the right side, and it has a single isolated diffusion contact there, so it needs a 2C capacitance added. However, the leftmost transistor, PMOS transistor, has VDD on its left side and its output on the right side, but the middle transistor has VDD on its right side and the output on its left side. So it is actually sharing a output contact with the leftmost PMOS, and the middle PMOS are sharing an output contact. So instead of each of them having a 2C capacitance, diffusion capacitance, they only have a single 2C capacitance. So this reduces the amount of total capacitance on the output node. Likewise, the NMOS diffusion, since the NMOS transistors are connected in series with each other, they can get their connection strictly through the diffusion itself. They don't need to have metal contacts and have separate drain and source. They can have a merged drain and source that actually causes that area between the two gates to be smaller than it used to be, and so that capacitance value can actually be less than it would have been. And in this particular figure, it's showing that instead of having a 3C from the source of one transistor and a 3C from the source of the other one, adding up to 6C, saying there's a total of 3C there. In reality, it would probably be even slightly less than that, because since you don't need a contact between those two gates, the area of that source drain area is slightly smaller than even a single contacted source drain area would be. So that 3C value would probably be even less than 3C by a slight amount, maybe 2.5C or something. So that can reduce your overall capacitance that you need to drive, both for pulling up and for pulling down. This shows an example of a 2-input NAND, and just look at it for a second and decide for yourself which layout is better, the layout on the left or the layout on the right. We'll pause here for a second. So if you look at it carefully, on the left, the NMOS devices in green are identical to the right. The main difference between the layout on the left and the layout on the right is for the VDD connection and the output connection to the PMOS transistors. The layout on the left has a single contact to the output and 2 contacts to the VDD in order to get the connection of each transistor to VDD and the output. And the layout on the right has a single contact to VDD and 2 contacts to the individual contacts to the output node. So the layout on the right has more capacitance on the output node, and the layout on the left has less capacitance to the output node. So in general, the layout on the left would be better as far as getting a shorter delay and quicker propagation delay through the gate.